Morning to everyone. Myself T. Muthukumar, Assistant Professor, Kongunadu College of Engineering and Technology. Today, I am going to deliver a lecture on Van de Graaff generators and electrostatic generators in the high voltage engineering subject. So, Van de Graaff generators and electrostatic generators. So, one of the method of generating high DC voltages. So, first I will explain the working principle and the operation of Van de Graaff generators and then electrostatic generator. Van de Graaff generator works under the principle of electrostatic machines. So generally we have the two types of principles. One is electromagnetic machines, another one is electrostatic machines. In electrostatic machines, charged particles, that is charged bodies, are moved in an electric field against the electric field. So on that process, electric energy is generated. For in case of electromagnetic machines, so current carrying conductors are moved in a magnetic field, so that mechanical energy is converted into electrical energy. So if you consider electromagnetic machines means variable conductors, that is current carrying conductors, are placed in the magnetic field. So these current carrying conductors changes the rate of change of flux. So automatically EMF will be induced in the machines. This is called electromagnetic machines. Faraday's law of electromagnetic principle, it works. So in electrostatic machines, here charged particles are moved in an electric field. So we are going to create the electric field. In this electric field, charged particles are moved means, so automatically our mechanical energy is converted into electrical energy. So this is the principle of electrostatic machines. So Van de Graaff generator is to generate the high DC voltage. So this will be works under the principle of electrostatic machines. So in Van de Graaff generator or electrostatic machines, so we are going to use the moving belt arrangement. So if an insulated belt with a charge density del, so we are going to use the insulated moving belt. The density of the charge is del. It moves in an electric field E of x. So electric field value is equal to E of x. So charge density del, electric field intensity E of x. So between the two electrode with the separation S. So belt is moves between the S distance with in an electric field E of x with a charge density of del. So the charge on the strip of the belt at a distance dx is dq. So charge on a belt at a distance dx is dq. So dq is equal to del into b into dx. So dq plus charge on the strip of is equal to dq is equal to del into b into dx. So del is called charge density, b width of the breadth, so ds is the distance. So our belt is moving with a charge density of del between the electrodes separation distance s in an electric field E of x. So dq is equal to del b into dx. So next, the force on the belt. So F is equal to, so integration of limit 0 to S, that is the distance 0 from S, E of x into dq. So this is the formula for force on the belt. So integral 0 to S, E of x into dq equal to, so 0 to S. So we are going to apply this dq value. Here dq is equal to del v dx. So our equation can be written as 0 to S del into d into E of x into dx. So this is the force on the belt. So this force is called mechanical force. The force required to move the belt from the distance 0 to S is converted into electrical energy. This is the principle of electrostatic machine. The force required to move the belt is converted into electrical energy. Okay, this is called electrostatic principles. So this force is converted. So force record and power record. If a belt is moves with a velocity v, then mechanical power P required to move the belt is the power required to move the belt is written as F is equal to, that is P is equal to mechanical power required to move the belt F into V velocity. So power is equal to force into velocity. So mechanical power is equal to force into velocity. So if you apply the force equation in this power equation, means the force already we discussed, force is equal to integral 0 to s del b e of x into dx. So this equation become del b into velocity integral 0 to s e of x into ds. So this is the power required to move the belt from 0 to s. So this is mechanical power. So this mechanical power is converted into electrical power. So that is power is equal to VI. So this is electrical power. So mechanical power is equal to F into V velocity, force into velocity. Here voltage into current. So current in the system. So generally we are writing the current equation. Current I is equal to dq by dq by dt. That is the rate of change of current. Charge, rate of change of charge is called current. So I is equal to dq by dt. So that's equal to dq is equal to del b dx divided by dt. So velocity means velocity is equal to dx by dt. So we are going to replace dx by dt as velocity. So finally the current value, current in the system becomes del into b into v. So I is equal to del into b into v. Del is called current charge density. V width of the belt, V is small v is called velocity. So next potential difference. So V is equal to 0 to S into E of x into ds. This is the potential difference. So power is equal to VI. So mechanical power required to move the belt is converted into electrical power. Power is equal to VI. So I is equal to del B into V. V is equal to 0 to S E of x into ds. So thus, in electrostatic machines, mechanical power required to move the belt is power is equal to F into V is converted into electrical energy power equal to V. Here, so we are going to assume so no losses in the system. So losses in the system will be negligible in this system. So this is the basic principle of electrostatic machines. So this is a construction diagram of anti-grav generator. These are the parts of the anti-grav generator. So this is called lower spray point. So in this point only we are going to spray the charge. This is called lower spray point. So part number 2 is called motor driven pulley. So this pulley drives the belt. Then only the belt moves from lower electrode to higher electrode. So this is called insulated belt. So this belt is insulated. This is insulated belt. This belt only carries the charges between the electrodes. So fourth one is called high voltage terminal. So fourth one is called high voltage terminal. This is called high voltage terminal. So part number 1 is called lower spray point. That is the lower low voltage terminal. So part 4 high voltage terminal. So number 5 is called collector. So this point. So these positive charges will be collected in the high voltage terminal. So sixth one is upper pulley insulated from the terminal, upper pulley. So this is upper pulley insulated from the high voltage. So seventh one is upper spray point. So this is upper spray point. So last one is earthed enclosure. So last one is earthed enclosure. These are the parts of the anti-grav generator. So it has a 2 electrodes. One is the lower electrode. This is high electrode, also called lower spray point and higher spray point. And 2 pulleys, lower pulley. Another one is high. Another one is higher pulley. So this is motor-driven pulleys. So driven by the electric motor. So fourth one is high voltage terminal. So fifth one is collector. So collector collect all the charges. So seventh one is upper spray point. So eighth one is enclosed sub. Total this setup is enclosed or earthed earthed by the system. So overall system is earthed enclosure, earthed in system, overall system. So next we will discuss the operating of, that is working of anti-graff generator. So this is used to generate high DC voltages. So we are going to spray the charges in the lower spray point. So this charges will move to the higher electrode. The higher electrode terminals collect the higher voltage potentials. And the belt moves from lower pulley to higher pulley. So the generator is generally, the overall system will be generally enclosed in an earthed metallic cylinder. So it is a enclosed by the earthed metallic cylindrical vessel, and it is operated under pressure air vacuum. So this generator operated under the pressure and vacuum conditions. The charge is sprayed onto the insulating moving belt at a potential of 10 to 100 kV. So we are going to spray the charges in the lower spray point. So in this point, lower spray point, so at a potential of 10 to 100 kV above the earth. So, and these charges are moved to the upper pulley. So at the nearby the high voltage electrode, it will be removed and collected from the belt connected to the inside of the insulated metal electrode. So it is collected by the high voltage within the collector. And then again belt moves with the opposite charged particles. So the belt is driven by electric motor with a speed of 1000 to 2000 meters per minute. So the belt is, so upper and lower pulley will be driven by an electric motor at a speed of 1000 to 2000 meters per minute. The potential at high voltage electrode above the earth at any instant. So potential is at high voltage electrode is very high at earth conditions at any instant. So formula V is equal to Q by C. V is equal to Q by C. The potential at the high voltage electrode. The rate of change of high voltage potential at the high voltage electrode is dV by dt is equal to I by C. So in that, so the overall system is enclosed with a metallic cylindrical vessel, and the system is operated under pressure or vacuum condition. So lower voltage is sprayed at the level of 10 to 100 kV. Lower charge is sprayed on the lower spraying point. So this charge is moved through the belt from high voltage to high voltage electrode from low voltage or lower spray point. So the collector collects all the high voltage charges at the high voltage terminal. The belt is driven by an electric motor with a speed of 1000 to 2000 meters per minute. The potential at the high voltage terminal V is equal to Q by C. The rate of change of potential dP by dt is equal to I by C. So next, the steady potential will be attained at the high voltage electrode. Here the steady potential will be attained at the high voltage electrode when the leakage currents is equal to load current and charging current. So leakage current and load current is equal to charging current means, so our high voltage terminal reaches the steady potential. The shape of the high voltage in the terminal is made with re-entrant edges. So this shape is with the re-entrant edges to avoid the high surface field gradient, corona and other local discharges. So to avoid the high surface field gradient, corona and other local discharges, the special design is made in the high voltage electrode, that is a re-entrant edges. So this avoid this corona and other local discharges and also high surface field gradient. Generally, the shape of the electrode is nearly spherical. So this shape of the high voltage electrode is nearly spherical. So the charging of the belt is done by lower spray point here. So with the help of the lower spray point, we are going to spray the positive charges in the lower spray point on the belt. So with the help of the sharp needle connected to the DC source. So this is the DC source. So this value is 10 to 100 kV voltage. So the positive charges, that is charges will be spread in the lower spray point. So this moves to the belt. So the corona is maintained between the moving belt and the needles. So corona is maintained between the needles and the moving belt. So the charge from the corona points, that is the lower spray point, is collected by the collector needles from the belt. So with the help of this collector needle, the charges are collected and transferred into the high voltage electrode as the belt enter into the high voltage electrode. So once the belt carries the positive charges, so collector in the high voltage electrode collect all the positive charges into high voltage electrode side. The belt returns with the charge dropped. So all the charges are collected from the received from the high voltage electrode. So then only the belt returns with the charge dropped and a fresh charge is sprayed on it. So fresh negative charges will be, after collecting the positive charges in high voltage electrode, the negative charges will be sprayed into the belt on the surface. So this is the second corona point, that is the lower corona point. So usually in order to making the charging more effective, so utilize the return path of the belt for charging purpose. So we are going to utilize the return path also for charging purpose. So self-inducing arrangement or second corona point system excited by the rectifier in the high voltage terminal. So second corona point or self-excited system will be induced by the rectifier side inside the high voltage terminal employed. So lower spray point sprays the positive charges that will be moved to the higher electrode through the belt. So collector collecting all the charges and negative charges, that is opposite charges, will be sprayed onto the upper spray point. So this is useful for the improving the charging purpose. So two corona points only available. One is lower corona point, another one is high voltage corona point. So to obtain the self-charging system, the upper pulley is connected to the collector needle. So upper pulley is connected to the collector needle. So and therefore maintained at a higher potential than the high voltage terminal. So we are going to obtain the self-charging system means upper pulley is connected to the collector. This collector is maintain the potential higher than the high voltage electrode terminal. So second row of corona points connected to the inside of the high voltage terminal. So this second corona point is connected inside the high voltage terminal towards the pulley above the point of entry. So this neutralizes the any charges on the belt and leaves on excess of opposite polarity to the terminal. So this neutralizes. So second corona point in the high voltage terminal neutralizes any charge on the belt and leaves on excess of opposite polarity to the terminal to travel down the belt. So negatively charged particle moves towards the lowest corona point. So bottom charging point. Thus for a given belt speed, the rate of charging is doubled. So with the help of this belt speed, rate of charging will be improved. So charging current for unit surface area of the belt is given by. So charging current in the belt I is equal to B into V into del. So B is the breadth of the belt, V velocity of the belt, del surface charge density in coulombs per meter square. So current charging current of the unit surface area of the belt is equal to I is equal to BV into del. So the generator is normally worked in a high pressure gaseous medium. We already discussed it works under the high pressure medium or vacuum. So high pressure gaseous medium, the pressure ranging from 5 to 15 atmosphere pressure. The gas may be nitrogen, air freezon, or CCl to F2 mixture, or sulfur hexafluoride SF6. So nitrogen, air freezer, CCl2, F2 mixture, or sulfur hexafluoride SF6. So this is the gaseous medium. So Van de Graaff generator are very useful for very high and low current applications. So this is used for the very high voltage and low current applications. So output is easily controlled by controlling the corona source voltage and the rate of charging. So output of the generated voltage easily controlled by corona source voltage and the rate of charging. The voltage can be stabilized to 0.01%. So these are extremely flexible and precise machine for voltage control. So stabilization voltage can be stabilized to 0.01%. So these are extremely flexible and precise machines for voltage control. These are the few advantages of or applications of Van de Graaff generator. So next, I'm going to discuss advantages. So with the help of this Van de Graaff generator, very high DC voltage can be generated. The output will be ripple free. Also, precision and flexibility of control is possible. So next, stability of the voltage can be achieved with a suitable stabilizing devices. So stability is control is also simple. So it is possible to generate high voltage, ripple free output, precision and flexibility of control is possible. So stability of voltage can be achieved with a suitable stabilizing devices. So next one is limitations of the Van de Graaff generator. Low current output. So it is a high voltage, low current device. So it produces the low current output. Limitations on the belt velocity due to vibration. So velocity of the belt causes the vibration. If velocity is higher means vibrations will be more. So it is difficult to have an accurate grading of electric fields. So maintenance necessary due to mechanically stressed parts. So we are using the mechanical pulley belt arrangement. So maintenance necessary due to mechanically stressed parts. So disadvantages. To develop electrostatic machines with insulating cylindrical rotor can sustain preferably stable movement even at high speeds. So movement of the belt should be stable with the high speeds. So it is somewhat difficult. So it is one of the disadvantages. So used for low power devices. So it is only used for the low power devices. Applications: nuclear physics laboratories for particle acceleration study. Nuclear physics laboratory is using the nuclear physics laboratory for particle acceleration study. So with the help of the Van de Graaff generator, we are going to generate high voltage, low current DC voltage. So next, so I'm going to move for electrostatic generator. So electrostatic generator. So Van de Graaff generators are essentially high voltage, but it is a low power device. So it is only used for the low power applications. So under the power rating, few tens of kilowatts. So it is not possible to use the high power sites. So we are going to discuss the another generating type. So there is electrostatic generator. So in electrostatic machines, which effectively convert the mechanical energy into electrical energy using the variable capacitor principle concept. So using variable capacitor principle concept, mechanical energy is converted into electrical energy. These are the duals of electromagnetic machines. So it replaces the electromagnetic machines and our constant voltage variable capacitance. So this is the duals of, that is, it replaces the electromagnetic machines and constant voltage variable capacitance machines. So because it is a variable capacitor principle, what comes with the variable capacitor? So this replaces the above two machines, electromagnetic machines and also constant voltage variable capacitance machines. So electrostatic generator consists of stator with interleaved rotor vands forming a variable capacitor and operates in a vacuum. So basically electrostatic generator means it consists of a stator with interleaved rotor. So rotor is a interleaving type forming a variable capacitance. So in rotor side, a variable capacitance will be formed. So this also operated in vacuum. This works under the principle of variable capacitor principle. So current through a variable capacitor. So I is equal to C into dV by dt plus V into dc by dt. So C is a capacitor charged to a potential V. So I is equal to C into dV by dt plus V into dc by dt. This is the current formula. So power input to the circuit. So power is called VI. So we are going to multiply above this equation by V. So CV into dV by dt plus V square into dc by dt. So this is the power equation in the system. So if dc by dt is negative means, so this dc by dt is negative means, so mechanical energy is converted into electrical energy. So if dc by dt is negative means mechanical energy is converted into electrical energy. With charged capacitors, the capacitor charged with a dc voltage V, so dc by dt is equal to 0. So if the capacitor is charged to maximum voltage V means dc by dt is equal to 0, then power output is equal to P is equal to V square dc by dt. Power output equal to V square dc by dt. So power is equal to Vi, power output equal to V square dc by dt. This is the power formulas and the current formulas in electrostatic machines. So next we are going to discuss working principle of electrostatic machines. So this is the construction diagram. So this has the interleaved stator and rotor vanes. So here this is stator. So stator with vanes. So this is the stator side, stator with van. So this is the rotor with interleaved vanes, rotor vanes. So A and B are the rectifiers. So A and B are the rectifiers. So this is the rotor plate voltage. We are going to maintain plus or minus V, rotor plate voltage. So here E is called line voltage output. This is the output. So this is the construction of electrostatic generator. So stator and rotor interleaved vanes are there. So rectifiers are there. Two rectifiers A and B are there. So we are giving the rotor plate voltage plus here. So output is equal to so minus E line voltage the output. So here the rotor is insulated from the ground. So this rotor is insulated from the ground and is maintained at a potential of plus V. So rotor is insulated from the ground. So here maintained the voltage is plus V. The rotor to stator capacitance varies from Cm to C0. So rotor to stator capacitance varies from Cm to C0. Here stator is connected. The stator is connected to a common point between the two rectifiers A and B, and the DC output is minus E volt. So here stator is connected, rotor is grounded and maintain a potential plus V. So stator is connected between the common point of rectifiers A and B with a output voltage of minus E volt. So if C equal to Cm, that is capacitor is equal to Cm, then rectifier B does not conduct. So if C is equal to Cm condition, if C is equal to Cm, so rectifier B does not conduct and stator is ground potential. So stator is at ground potential. So then E is applied across the rectifier A. So this E is applied across the rectifier A and V is applied across the Cm. So and V is applied across the Cm. That so rotor capacitance V is applied to the Cm rotor capacitance. As the rotor rotates, so this rotor is rotates, the capacitance C changes, that is C decreases and the voltage across C increases. So capacitance decreases means the voltage across the C increases. Thus, the stator becomes more negative with respect to the ground. So if C is equal to Cm, so rectifier B does not conduct. So E is applied across the rectifier A, which is applied to the across the Cm. So at the rotor rotates, the capacitance C decreases and the voltage across C increases. So stator becomes so negative with respect to ground. So when the stator reaches the line potential minus E, so once it reaches the maximum voltage minus E, the rectifier A conducts and further movement of rotor causes the current to flow the generator. So current will be induced in the generator. This is the working of electrostatic generator. So it works under the principle of variable capacitance. So finally, I'm going to conclude this topic with the help of recall. So Van de Graaff generators works on the principle of electrostatic machines. Here, the force required to move the mechanical power required to move the belt from one place to another place is converted into electrical energy. That is P is equal to FP. That is mechanical power is converted into electrical energy. That is electrical power VI. So this principle is called electrostatic principle. So Van de Graaff generator used to generate high voltage in the DC. So it works under the principle of electrostatic machines. So these are the parts of electrostatic generator. So it has two electrodes, lower electrode. This is higher electrode. So this is in the sphere shape. So in lower spray point, we are going to spray the positive charge. So in the range of 10 to 100 kilovolt. So the belt will be driven by a belt-driven arrangement of electric motor. So it moves a speed of 1000 to 2000 meters per minute. Though this belt carries the positive charges once the belt moves from lower spray point to higher spray point. So collector collect all the charges in the high voltage side. See if the steady state potential is achieved. So when leakage current is equal to charging current. So once high potential is achieved, so all the charges will be collected from the belt in the high voltage side. So with the help of self-inducing system, it produces oppositely charged particles. This opposite charges moves through the belt for improving the charging purpose. So this is the working of Van de Graaff generator. So shape of the high voltage electrode is nearly sphere shape to avoid the corona and other local discharges and high surface field gradient. So advantages. So it is used to generate very high DC easily, ripple free output, precision and flexibility of control. Stability of voltage control can be achieved with suitable stabilizing devices. Limitations: low current output. So velocity increases mean vibrations will be biggest issue. So it is difficult to have an accurate grading of electrical fields. Maintenance is necessary due to mechanical stressed parts. So disadvantages. So we are going to sustain the stable movement even at high speed. That is one of the disadvantage, and also it is used for only for the low power devices. So applications: nuclear physics laboratory for particle acceleration study. So next, electrostatic generator. So electrostatic generator is to produce the high power, because Van de Graaff generator only for the low power rating generator. So it is replaces the electromagnetic machines and also constant variable voltage capacitant machines. So there is a works under the principle of variable capacitance principle. So it has the stator and the interleaved rotors and works under the operated under the vacuum conditions. So stator, rotor will be interleaved nature. So rotor is maintained at the ground potential. So stator is connected to the common points of the two rectifiers A and B and maintain the voltage minus C. So if rotor is rotates, means the rotor capacitance will be varies. So if rotor capacitance will be decreases, means rotor or induced voltage will be increases. This causes a current flow of the generator. So this is the working principle of Van de Graaff generator. So in this lecture, so I discussed two important DC high voltage DC generators. One is Van de Graaff generators. So another one is electrostatic generators. Thank you.